get right into an application that a lot of people are probably familiar with. If you wear glasses, or if you know someone who wears glasses, if you kind of look at them a certain way, you see like a little greenish tinge on the top. That's part of the anti-glare coating. So a lot of people who wear glasses have what's called an anti-glare coating. And the reason people get that is it removes some of the light, some of the glaring light that you have with glasses that don't have the coating. So the way that works is you take your glasses, you put a little film on the top, and you put the kind of film and the thickness of film on there in such a way that it would maximize destructive interference. That's what takes away the glare. So let's kind of go through this process as an example in an application all in one go. So we have light with wavelength lambda. That wavelength lambda refers to the light in a vacuum or in air. It's incident on a glass. The index of refraction of glass we'll call Ng. And the glass is coated by a thin film of anti-reflective coating that has a thickness D. So from here to here is thickness D. And we're going to sort out what D has to be. And the coating has an index of refraction that we'll call N with a C on it. So let's think about the reflected light in general. We'll think about light coming in, light bouncing off. Let's write down the conditions for constructive and destructive interference, and then we'll apply some numbers in an example. So what we have in this setup, outside of the glass with the thin film, is air. And the index of refraction for air is 1 or almost exactly 1. So now what do we have that happens? Let's think about the light waves. So we have some incident light. So the light comes through the air and it hits the coating. So the light comes in like this. There's our light wave coming in. The light wave that comes in, part of that goes on through. So part of that light wave goes on through, but part of that light wave reflects. Okay? So that's the light reflection that we've been talking about. This goes from an area where n equals 1 to an area with NC. NC is going to be bigger than 1 because all indices of refraction are bigger than 1 except for air and vacuum. So N air is less than NC. So that's the same case as when we go from like a light string to a heavy string. This is like a fixed boundary, so when it reflects it inverts and we get a phase shift of pi. So this wave is out of phase compared to this one by pi radians. Okay, so that's what happens at that first boundary. At this second boundary, part of the light goes on through, and of course I should be drawing this all in a line, but it just gets too cluttered. Of the light that hits here, part goes through and part of it rebounds, so part of it comes on back through here. For this light wave, we're going from NC to NG, from coating to glass, and we have our coating index of refraction is less than our index of refraction as glass. That's the typical kind of coatings for glasses, so we're going to say that NC is less than NG. So that again is like going from a light medium to a heavy medium. So when it reflects right here, this wave is going to invert. So that's going to have a pi phase change as well. So what we have, the air comes in, part of it reflects here, part of it reflects here, and each of those reflected waves go from light to heavy, so they get a phase change of pi. It shifts. Okay, so these two reflected waves, if somebody is standing right here, what the person sees is these two reflected waves. So let's talk about the constructive and destructive interference that the person sees because of these reflected waves. And maybe the first thing we're going to point out, because we'll be applying this for both constructive and destructive, is this wave had a shift of pi, this wave had a shift of pi, so these are actually both in phase. So if this one comes in on a crest, this one comes out on a crest, and this one comes out on a crest. So they both shift, no, hang on. If this one goes in on a trough, this one comes out on a crest, and this one comes out on a crest. Okay, so they're both opposite this guy, but since they're both opposite, these two have to be the same. So the two reflected waves are in phase. If the two reflected waves are in phase, we might start thinking about where we're going to go with this. It means delta phi naught equals 0. So the phase constant of this one is the same as the phase constant of this one. So if we subtract those two guys, we get 0. Okay, so next, let's think about the conditions for interference. For constructive interference, we know that the phase difference of the two waves has to be a multiple of 2 pi. So let's write that down. So if we want constructive interference for these two waves, so constructive, so this would be something we see, this is visible because it's constructive. The phase difference between the two waves is 2 pi over lambda times delta x plus delta phi naught equals m times 2 pi, where m equals 0, 1, 2, and so on. Okay, this is our general expression. Let's apply this expression to what we're talking about here. So the first thing we should think about is, what do we mean by lambda? The lambda we have is the lambda inside the material. So actually, why don't we even do delta x first? So delta x is the path difference. It's how much further this wave goes compared to this wave. So how much further this wave has to go is that the light has to come in and it has to turn around and come back. So this light right here, it hits the boundary, comes off right away, but this one, it had to go in and come all the way back. So this wave had to come in, turn around, and come back. So delta x is still path difference. And it had to come in, then come back, so it's equal to 2 times the thickness of the glass. So it had to travel to the right, then it had to turn around and travel to the left, and that's how much farther this one goes compared to this one. So since delta x is the path difference inside the coating, the lambda that we have to be concerned about is the lambda inside the coating. So our lambda equals lambda in the coating. So our lambda for our constructive interference here. So we're going to call that lambda n for the coating. And then hopefully you remember that to get a wavelength in a coating, what we do is we take the wavelength in air or in the vacuum and divide it by the index of refraction. So now let's write in the things that we know. Lambda equals lambda nc. Delta x is the path difference. Delta x equals twice the thickness of the coating. Delta phi naught is the relative phase constants of those two waves. They're the same, so delta phi naught is 0 and m is our set of integers. So if we have a coating on a pair of glasses or on glass, and we have that the index of refraction of the coating is less than the index of refraction of the glass, then our condition for constructive interference is equal to 2 pi over lambda in the material times twice the thickness of the coating equals m times 2 pi. So this is constructive where n of the coating is less than n of the glass. We can do this treatment as well, but we can think about destructive. So what light would we not see? So anything that matches this condition, so anything that where we relate the d and the lambda would fit this equation, is something that we're going to see. If we want something we don't see, so what color would we never see? That would be our destructive interference. For destructive interference, delta phi is 2 pi over lambda times delta x plus delta phi naught equals m plus 1/2 times 2 pi. We can fill in the things that we know here. So lambda is the wavelength in our coating. Delta x is how much further this wave goes compared to this wave. So that's our path difference. It's 2 times d. And delta phi naught is the initial phase difference of those two waves. Those two guys are in phase, so delta phi naught is 0. Same conditions as we had before. And here m is exactly the same set of integers, 0, 1, 2, and so on. So for destructive interference, delta phi is equal to 2 pi over the lambda inside the coating times 2d equals m plus 1/2 times 2 pi. This is how you get destructive interference when the index of refraction of the coating is less than the index of refraction of the glass. Okay, now the next thing we can look at is an example with some actual numbers in it. Let's have a look at that guy. So let's take a pair of glasses, a typical thin film, together knowing what the index of refraction is, and see if we can figure out how thick that film should be. So let's say on the pair of glasses our optician is making for us that we want to minimize, so let's circle that word because that's pretty important. We want to minimize the reflection of blue-green light. Blue-green light has a wavelength in air or vacuum of 510 nanometers. We're going to minimize that by putting a magnesium fluoride film on the glass. The index of refraction of the magnesium fluoride film is 1.39. How thick of a film should we put on those glasses? Okay, so we won't invent the wheel again. So we want to minimize the reflection. So right off the bat, we're talking about destructive interference. Let's write down that equation. So minimize means destructive. Destructive means that delta phi is equal to 2 pi over lambda inside the coating times delta x plus delta phi naught equals m plus 1/2 times 2 pi. Some special things that we know. Lambda inside the coating is lambda in air divided by the n of the coating. Delta x is twice the thickness of the glass, so it's the path difference. It's how much further this wave goes compared to this one, so it had to go in and come back out. Delta x is 2 times the thickness. Delta phi naught has to be 0 because these two reflected waves are in phase, and that's true whenever the coating has a smaller index of refraction than the glass. Okay, so let's put these conditions in our equation and see what we get and see if we can find our thickness. So delta phi equals 2 pi over lambda in air times the index of refraction of the coating times 2d plus 0 equals m plus 1/2 times 2 pi. What will we put in for our m value? Well, in general, when you have glasses, you don't want that much gunk on top of them, so you want the smallest film you could possibly have. So the film you'd like to have is the m equals 0 layer, because you want a thin film. Okay, so 2 pi over lambda times n times 2d plus 0 equals 1/2 times 2 pi. What I see right off the bat is I have 2 pi on either side, so I'll divide both sides by 2 pi. I'm trying to sort out what my thickness is, so I'm trying to solve for d. So then d is going to be 1/2 times times lambda divided by 2 times the index of refraction of the coating equals lambda over 4 times the index of refraction. Or if you wanted to think about this in terms of being the wavelength inside the film, you could write it this way if you wish. It's not mathematically beneficial, but conceptually you might like to think of it that way. So our wavelength lambda is 510 nanometers, so 510 times 10 to the minus 9 meters, divided by 4 times the index of refraction, which is 1.39, equals 91.7 times 10 to the minus 9 meters, or 91.7 nanometers. So if your coating has an index of refraction that's smaller than your glass, if you want to minimize the reflection, you need a film that's a quarter of the wavelength. Wavelength of light is very small, so what this kind of tells me is that optical technology is really pretty fascinating, so the opticians must be very talented as well as the engineers who designed all this stuff.